End-to-end supply chain analytics project. In this lesson, we solve a real-world supply chain analytics problem using real data. Supply chain analytics helps businesses optimize inventory, demand, supplier performance, and order fulfillment. Understanding these analytics is essential for reducing costs and improving service levels. You will learn to load, explore, join, and analyze supply chain datasets from procurement to delivery. You will gain skills to spot mistakes, build metrics, and communicate operational insights. Running the cell now. We import pandas for working with data frames. We import OpenML to load public real datasets directly from OpenML. We import NumPy for numerical operations in analytics. We import Matplotlib for making supply chain charts and plots. We import Seaborn for more visually compelling analytics plots. We import warnings to help us ignore warning messages in this notebook. We tell Python to ignore warnings so analytics output is cleaner. Running the cell now. Understanding supply chain and operations data. Supply chain data often includes orders, inventory, demand, supplier performance, and deliveries. Data may be structured as transactions, logs, or status snapshots over time. Common mistakes include misinterpreting dates, confusing product IDs, or ignoring missing data. Consistent formatting and date parsing are especially important. Running the cell now. In this step, we load a real retail demand transactions dataset to analyze historical sales activity. We add a comment for this beginner example and explain our objective. We specify the URL of the UCI online retail transactions dataset. We load the dataset into a pandas data frame. We parse the invoice date column into proper datetime format. We print the shape of the data frame to see how many records and columns are loaded. We display the first 3 rows to check the transaction fields. Running the cell now. This output shows the loaded retail demand dataset with over 500,000 rows and 8 columns, including key supply chain fields like invoice date, stock code, quantity, and price. Notably, the invoice date column has been successfully parsed into a datetime format, ensuring accurate time-based analysis. This step is essential for avoiding common mistakes such as misinterpreting dates in supply chain data. Practice. Try viewing 5 or 10 rows of this data frame. What are the columns telling you? Now we will load supplier performance data, a critical operations dataset for supply chain analytics. We comment what this beginner example covers. We load the supplier performance dataset from OpenML. We extract the pandas data frame from OpenML data. We print the supplier data frame shape to know the record count. We print the first 3 rows to preview the supplier metrics. Running the cell now. The output shows that the supplier performance dataset contains 9,228 rows and 13 columns, indicating a sizable tabular dataset. Key columns include employee details like full name, gender, salary, department, and hire date, which are crucial for analyzing supplier workforce and performance trends. This aligns with the lesson's focus on understanding structured operations data, highlighting the importance of consistent formatting, e.g., parsed dates, and clear columns for meaningful analysis. Think, what key metrics might operations managers look for in supplier records? Order fulfillment is central to understanding supply chain performance. Let us load a real e-commerce orders dataset. We comment our intent to load an order fulfillment operations dataset. We set the URL where the OList orders data is hosted. We load the orders CSV into a pandas data frame. We convert order purchase time to datetime format. We also parse the actual order delivered date to date time. We print orders data frame dimensions. We check the first 3 order records for basic structure. Running the cell now. This output shows the orders dataset with 99,441 rows and 8 columns, including key timestamps like purchase, approval, and delivery dates. Notice how the date columns were successfully converted to date-time format, which is crucial for analyzing timing and delays in supply chain processes. Checking the first few rows helps confirm that the data is loaded and parsed correctly before deeper analysis. YouTube, watch how real companies analyze order fulfillment data for more insights. In operations, missing data can signal problems. Here we look for missing delivery records. We comment that this cell will detect missing order delivery dates. We check how many delivery date values are null. We print the number of orders that are missing a delivery date. Running the cell now. This output reveals that there are 2,965 orders in the dataset where the delivery date is missing, indicating incomplete delivery records. Noticing this gap is crucial because missing delivery dates can lead to inaccurate analysis of supply chain performance or customer satisfaction. This step highlights the importance of detecting and handling missing data to ensure reliable insights in operations management. Practice: what could cause some orders to lack a delivery date? Think about possible business reasons. On-time delivery rate is an essential KPI. Let us quickly summarize it for our suppliers. We note this cell calculates on-time delivery performance for suppliers. We test if the performance column exists so our code is robust. If present, we calculate the distribution of on-time late deliveries. We print the normalized counts, fractions, of on-time versus late deliveries. If missing, we warn the user that this field is unavailable. Running the cell now. This output alerts us that the supplier dataset lacks that on_time_delivery column, which is crucial for assessing delivery performance. It's a reminder to always verify that key columns exist before performing analysis, especially in supply chain data where missing metrics can lead to incomplete insights. Ensuring consistent data structure helps avoid errors and supports accurate performance evaluation. Try: what other supplier metrics would you want to summarize? Share ideas with your learning group. Operations teams often analyze daily demand patterns. Let us aggregate sales data by transaction day. We note in the comment that we will produce daily total sales quantity from the retail dataset. We group and sum total quantity sold for each day. We print the daily demand time series for the first few days. Running the cell now. This output shows the total quantity of retail sales aggregated by day, highlighting daily demand trends in the supply chain. Notice the grouping uses the date part of the invoice date, ensuring accurate daily summaries rather than timestamp details. This helps in understanding overall sales volume patterns, which is key for inventory planning and demand forecasting. Challenge: how might this output help you manage inventory or plan promotions? Order lead time is the time between order placement and customer delivery. Let us visualize the distribution in practice. We note this cell will plot the distribution of order lead times. We calculate lead time in days for each order using time delta. We set up the figure size for consistency. We plot a histogram and KDE of all available lead times. We add a descriptive plot title. We label the x-axis as lead time. We label y-axis for order count. We show the plot. Running the cell now. This histogram shows the distribution of order lead times, calculated as the days between purchase and delivery. Notice the range and frequency of lead times, highlighting typical delivery delays and variability in fulfillment speed. This helps in understanding supply chain responsiveness and identifying potential bottlenecks or delays in order processing. YouTube explores mastering lead time analytics in Python for step-by-step operational guidance. Order fulfillment often depends on matching supplier records to individual orders. Here, we simulate this process. We add a comment that we are simulating an order and supplier join operation. We check if both data frames have a supplier ID column to join on. If so, we merge orders_df with supplier_df on supplier ID using a left join. We display selected columns to verify the join was successful. If not, we let the learner know no common key is available. Running the cell now. This output highlights a critical check in the lesson on merging supply chain data, the presence of the join key, supplier ID, in both datasets. Since supplier ID is missing from one or both data frames, the join cannot proceed, preventing errors or misleading results. This reinforces the importance of verifying key columns and consistent data structure before merging transactional and supplier data. Practice: why is it risky to merge on the wrong key? Think through possible operational errors. Retail operations use moving averages to smooth volatility in daily demand. Let us visualize trends with real data. We comment on calculating a 7-day moving average for retail demand. We ensure daily data is time-sorted for rolling computations. We compute a 7-day rolling mean, with a minimum of 1 day initially. We set up a wide figure for the plot. We plot the original daily demand as a line. We plot the 7-day moving average over the original. We add a legend to distinguish the lines. We label x-axis as date. We label y-axis as units sold. We give the plot a descriptive title. We display the plot. Running the cell now. This plot shows daily retail demand alongside its 7-day moving average, smoothing out short-term fluctuations to reveal underlying trends. Notice how the moving average line is less volatile, making it easier to identify demand patterns over time, which is crucial for reliable supply planning. The consistent date index ensures accurate windowing and trend analysis in the time series data. Practice: try different window sizes for the moving average and note the business impact. Regional analysis is important for global supply chains. Here we evaluate supplier performance by region. We describe that we are analyzing supplier performance by region. We check for presence of both region and on_time_delivery in the data. If available, we calculate the average on-time delivery rate per region. We print the aggregated regional performance results. If unavailable, we notify the user about the missing columns. Running the cell now. This output indicates that either the region or on_time_delivery columns are missing from the supplier data, preventing regional performance analysis. This highlights the importance of verifying column presence before grouping, a key step to avoid errors when working with supply chain datasets that may vary in structure. Ensuring consistent column naming and availability is crucial for accurate supplier performance evaluation. Challenge: how could this output help managers allocate more business to top-performing regions? Operations leaders need to quickly identify abnormal delivery times. Here we use the 3 Sigma rule to spot outliers. We comment our intent to identify abnormal delays in order lead times. We calculate the mean lead time. We calculate the standard deviation of lead time. We create a mask for lead times greater than 3 standard deviations above the mean. We filter for these potential outliers. We print how many outlier orders were found. We show several example outliers for review. Running the cell now. This output highlights that 1,614 orders have lead times significantly higher than average, identified as potential outliers using a 3 standard deviation threshold. Noticing the high lead times, ranging from 49 to 81 days in the sample, is critical for supply chain analysis, as such delays could signal bottlenecks or issues with supplier performance. This reinforces the lesson's focus on careful data inspection to detect anomalies that impact operations. Practice: what operational steps might you take if you see a sudden rise in delivery lead time outliers? Missing transaction dates break time series analytics. Let us explicitly check for this common data issue. We mark this code cell for error handling. We measure how many rows have missing invoice date values. We print the number of problematic rows. Running the cell now. This output tells us there are no missing values in the invoice date column, which is crucial for accurate time-based analysis in supply chain data. Ensuring no missing dates helps avoid errors in tracking orders and deliveries over time. This check confirms our data is clean and ready for further date-dependent operations. Remember, always check for missing key dates before time-based operations. If order IDs are duplicated, joins can create big problems. Let us validate that order IDs are unique before joining. We comment about error handling for duplicate keys. We count duplicate order_ID values in the order's data frame. We print the occurrence count for problematic duplicates. Running the cell now. This output shows there are 0 duplicate order IDs in the order's data, confirming each transaction is uniquely identified. This is important because duplicate keys could cause errors or inaccuracies when joining orders with other data tables, such as inventory or deliveries. By verifying this upfront, the code helps ensure reliable, clean data integration for analyzing supply chain operations. Always check key columns for uniqueness before merges or joins. Negative quantities can mean returns or mistakes. Let us check for them in retail data. We flag this cell for an inventory error check. We filter for rows where quantity is negative. We print the number of such records detected. Running the cell now. This output reveals that there are 10,624 records with negative quantities in the retail data, which likely represent returns or errors. Noticing this count is crucial because negative values can affect inventory and demand analyses if not handled properly. This reinforces the lesson's emphasis on careful data validation and error handling in supply chain datasets. Returns and cancellations are natural, but mixing them with sales confuses analytics. A best practice operations KPI is average order fulfillment lead time. Let us calculate and communicate it clearly. We mark that we are calculating a key performance metric. We use pandas mean to aggregate order lead time. We print the result with 2 decimals for reporting. Running the cell now. This output shows the average order lead time, calculated as about 12 days, which tells us the typical delay between order placement and fulfillment. Notice the focus on the order_lead_time column, highlighting the importance of correctly calculating and interpreting time intervals in supply chain data. This metric helps identify potential bottlenecks and improve operational efficiency by monitoring delivery performance over time. What is a reasonable lead time for your own use case? Rolling KPI patterns help spot peaks and bottlenecks. Here we illustrate with order volume. We note another best practice, rolling KPIs for demand tracking. We count the number of order IDs per day. We calculate a 7-day rolling sum for weekly trends. We adjust the figure size. We plot the daily order counts. We plot the 7-day rolling count as a smoother line. We provide a title for the plot. We set the date on the x-axis. We set order count for the y-axis. We show the plot with a legend. Running the cell now. This plot reveals both daily order counts and their 7-day rolling sums, smoothing out daily fluctuations to highlight longer trends in order volume. Notice how the rolling line helps identify sustained increases or decreases in orders, which is crucial for managing inventory and anticipating demand in supply chain operations. This demonstrates the value of correctly parsing dates and aggregating data over time to avoid misinterpreting volatile daily figures. Rolling order count shows you both overall trend and short-term spikes in fulfillment workload. Group and count suppliers by on-time delivery to highlight strengths and weaknesses. We describe grouping suppliers by delivery performance. We check if the dataset has on_time_delivery values. We count how many suppliers fall into each performance group. We print the results. If unavailable, we explain the limitation. Running the cell now. This output tells us the on_time_delivery column is missing from our supplier data, highlighting a key data quality check in supply chain analysis. Without this field, we cannot evaluate supplier delivery performance, which is essential for tracking reliability. This error message reminds us to verify critical columns exist before proceeding with analysis. Grouping suppliers lets you identify vendors who need improvement and those who set the benchmark. Time-based grouping reveals when demand is strongest. Here we split retail sales by day of week. We reveal a time series analysis by extracting weekday from invoice date. We create a new column for weekday number. We group sales quantity by each day of the week. We print summed quantities for each weekday. Running the cell now. This output summarizes the total sales quantities by day of the week, revealing distinct patterns between weekdays and weekends. Notice that sales peak midweek, days 2 to 3, and drop significantly on the weekend, day 6, highlighting how demand fluctuates with the day. This helps us understand temporal trends in supply and informs inventory planning to match typical shopping behavior. Is your business busier on certain days? Use these insights for staffing and inventory decisions. Let us bring it all together, join retail demand to supplier performance and aggregate daily KPIs in one step. We begin the end-to-end analytic by checking if a supplier ID is available in both data frames. We prepare to store results in proj_results. We confirm both data frames have supplier ID for join. If so, we merge retail transaction orders with supplier performance. We ensure invoice date is in date time for aggregation. We group by day, collecting sum of quantities and mean of on_time_delivery. We assign the result to proj_results. We show a week of resulting metrics. If not possible, we inform the learner the join cannot be done. Running the cell now. This output highlights a common data issue. The missing supplier ID error key prevents merging retail and supplier data, so we cannot calculate combined daily KPIs like total quantity and on-time delivery rate. It underscores the importance of ensuring consistent key columns exist before attempting joins, a critical step in integrating supply chain datasets for meaningful analysis. End-to-end, you have now built a real supply chain analytics pipeline from order data to delivery KPI.